Hello. Well, we've arrived. This is the final video tutorial in the series of calculus videos for Mr. Billingham's AP/BC calculus class. It has my favorite meme at the end, and it is the calculus part of 11.3 polar coordinate calculus. So we're going to start off by finding a tangent line to a polar coordinate curve. So in example 5, we're asked to find the slope of the rose curve, r equals 2 sine 3 theta, at the point where theta equals pi over 6, and use it to find the equation of the tangent line. Now you might initially, instinctively want to calculate dr d theta, but that wouldn't be a slope of a line. That would be the rate at which the radius is growing as the angle is changing. Now I want to get dy dx, and fortunately there's a nice way to do that we just discussed in the last video. So we start off with any polar equation in the form r equals f of theta, and you remember that x is r cos theta, so multiply both sides through by cos theta and you'll get r cos theta is f of theta cos theta, and r sine theta is f of theta sine theta. So now we have expressions for x and y, and I can calculate dy dx as dy d theta divided by dx d theta. So in this particular example now I have two expressions for y and x both in terms of theta. So I'm going to calculate dy d theta and divide it by the calculation for dx d theta. We're going to be using the product rule and the chain rule here. So it's going to be a fairly lengthy calculation. Just pay attention to the details. So that's what I get for dy d theta and dx d theta. Now I'm going to divide them and set theta equal to pi over 6. So we calculate the slope is negative root 3. Now when theta is pi over 6, r is 2. So let's calculate the x and y coordinates of that point. Let's convert 2 pi over 6 to rectangular coordinates. And using the formula x is r cos theta, we get 2 times cos pi over 6, 2 times root 3 over 2, root 3, and sine pi over 6 is a half, so the coordinate is root 3, 1. So the equation of the line is, and here's a quick snapshot of the screen of a graphing calculator with both of these on it. And you can see it really does look like we've nailed the tangent line. So next we turn our attention to the areas enclosed by polar curves. We'd like to be able to use integration to find areas enclosed by polar curves, just as we did with curves defined by their rectangular coordinates. Converting the equations to rectangular is not always a reasonable option. So we'd like to have a formula that involves small changes in theta rather than small changes in x. Now a small change in x produces a little rectangular strip of area, while a small change in theta produces a thin sector of area. Think about that and see if that makes sense. You should recall from an earlier course that the area of a sector is given by 1/2 r squared theta. Now here the theta becomes d theta, and so the area, or the little incremental area, is 1/2 r squared d theta, and often we'll write this as 1/2 f of theta squared d theta. And if we integrate that from the first theta to the last theta, we will calculate the area inside a polar curve. So to sum up, the area between the origin and the curve f of theta, for theta between alpha and beta, is given by the integral from alpha to beta of 1/2 r squared d theta. Also can be written 1/2 f of theta squared d theta. Let's work an example. So we're going to find the area in the plane enclosed by the cardioid r equals 2 times the quantity 1 plus cos theta. We could graph this carefully by hand or using technology, but here's what the graph looks like. If we look at this maybe in a tracer form, as theta goes from 0 to 2 pi, we can see that the radius starts at 4 and then drops slowly as we go around counterclockwise until at pi the radius is dropped to 0, and then it grows again. So we're looking for this integral. Now this is an integral that we can do by ourselves without a calculator, especially if we remember a little trig identity to get rid of that cos squared theta. It's called a power reduction formula. So substituting in the power reduction formula, the integral becomes the following. Note here that the 2 in the denominator of 1 plus cos 2 theta over 2 and the coefficient 2 in front of cos squared theta canceled out. So this should be a pretty easy integral to do because all three parts are very easily integrable. So not too bad, and the area turned out to be exactly 6 pi. Just remember the formula, 1/2 r squared d theta, and you can do polar coordinate calculus. Let's do another example. In polar coordinates, whenever you're graphing of something of the form r equals a cos theta or sine theta plus b, if a is greater in absolute value than b, you get an internal loop called a limaçon. And the graph of this one looks as follows. Now, they're very kind in pointing out that the inner loop starts when theta is 2 pi over 3 and ends when theta is 4 pi over 3. But one thing that we need to at least consider is the fact that for those values of theta between 2 pi over 3 and 4 pi over 3, r is actually negative. For instance, at pi, r is 2 cos pi plus 1, which is 2 times negative 1 plus 1, and negative 1. So at pi, r is actually negative 1. But since the formula for the area is 1/2 r squared d theta, the radii squared will always be positive, and we don't have to worry about it. So our formula here is as follows. And again, this isn't a terrible integral to do by hand, but we can go ahead and use technology, and it turns out to be that the area of the inner loop is about 0.0544. So after we learned how to find the area beneath a curve, the next thing we learned back in integral calculus with rectangular functions was the area between two curves, and we're now going to cover that in polar coordinate calculus. This should make perfect sense, especially when you look at this diagram. In this, the diagram would be, the blue area would be the whole area of the sector, which is the integral from alpha to beta of 1/2 r2 squared d theta, minus that little white piece down at the bottom, which is the integral from alpha to beta of 1/2 r1 squared d theta. So, as you can see, the formula makes perfect sense. Let's work an example. Okay, we're finding the area inside a circle of radius 1 and outside a cardioid. So let's look at the graph. That will help us figure out limits of integration and the order in which is being squared from subtracted by what other square. So inside the circle and outside the cardioid is the gray area. The limits of integration are negative pi over 2 to pi over 2, and the integral we need would look something like this. We can exploit the symmetry here. We can just take the integral from 0 to pi over 2 and double it. And that finishes the content for the year in AP Calculus. So with some sadness, I'm signing off now. I hope we'll be able to stay in touch through video chats and some virtual classrooms and work some free responses together. Anyway, here's my favorite meme. So hang on to your seats. Looking at that makes me really miss being in the classroom and being with you guys. So stay healthy, stay well, prepare for that AP exam. You should be able to do really well. You're going to have an edge in using technology. You should have been well prepared. Just practice the free responses, turn in the assignments, get your grade as high as you can get it. And, you know, I hope college for you next year is a good experience, that we're not sitting out first semester still. But stay in touch, and I'll be opening up Teams chats on Fridays and Tuesdays. All right, bye-bye.